Basic code executes sequentially. The compiler reads instructions strictly from top to bottom, processing one line after another with no deviation. This rigidity hits a physical limit the moment we require massive repetition. Writing 500,000 manual print commands to generate specific outputs is an impossible structural bottleneck. The engineering solution to this bottleneck is control flow. It relies on two primary mechanisms: conditional branches for decisions and cyclical aeration to automate repetition. We are going to deconstruct the architecture of these mechanisms, trace how they interact with character memory, and use mathematical proofs to optimize execution speed. Programmatic autonomy requires the ability to adapt. If software cannot branch, it is locked into a single sequence that ignores live data constraints. This diagram illustrates a basic if statement. It acts as a decision gateway, evaluating conditions down to strict true or false Boolean states. By chaining if, else if, and else blocks together, we construct a cascading sequence of logic gates capable of filtering any incoming variable. Consider the problem of sorting text. We need a system that mathematically evaluates whether a user's keyboard input is an uppercase or lowercase letter. Look closely at this memory cell. C++ memory architecture stores characters as ASCII integer values. Underneath an uppercase A is the integer 65. Passed into a logic gate, implicit type conversion takes over. The compiler strips the character designation, extracting the underlying integer. The compiler now treats the input entirely as a number, allowing us to evaluate letters using standard mathematical operators. All uppercase letters map precisely to the numerical range between 65 and 90. Checking if an input falls within these boundaries isolates uppercase characters instantly. Mapping these abstract data types to their hardware memory reality lets engineers write logic that is mathematically rigorous. When a program needs to execute that logic thousands of times, we build loops. Every loop requires three structural components to function: initialization to set a starting state, condition evaluation to maintain the run, and state updation to modify the variables on each cycle. The condition acts as the failsafe. It monitors the updated state and tells the cycle exactly when to terminate. If the updation node is missing, the condition never changes. The processor enters an unbreakable cycle, repeating a redundant task and rendering the software unresponsive. In a standard while loop, this architecture evaluates the precondition before the code ever executes. Comparing these two structures side by side, the for loop consolidates all three nodes onto a single line of code, creating a highly readable, compact architecture. Alternatively, a do-while loop inverts the logic. It evaluates the post condition after the execution block completes. Watch the execution paths here. A standard loop will hit a false condition and immediately stop, doing zero work. By delaying its check, the do-while loop guarantees the execution block runs at least once. The exact structural position of the condition check dictates the runtime behavior and safety limits of the iteration. Let's test this architecture against a mathematical challenge, determining if a number is prime by checking its divisibility between 2 and n-1. This standard for loop illustrates a naive approach. To test the number 12, it iterates sequentially, dividing by every integer from 2 up to 11. This requires n-2 distinct operations. Scanning millions of numbers sequentially like this creates an enormous system-slowing processing bottleneck. We bypass this bottleneck by mapping the mathematical factors. Here is the full grid of factor multiplication pairs for 12. There is an exact mathematical inflection point located precisely at its square root. Factors beyond this line are mirrored duplicates. Updating our loop to stop here drastically prunes the search space. Any potential divisor will appear before the square root, eliminating the need to check the remaining linear range. Once we detect a single clean division, we issue a break command. The program immediately snaps out of the cycle structure, abandoning any remaining checks. By anchoring syntax limits in factor symmetry, engineers remove linear bottlenecks and achieve sublinear efficiency. Control flow provides the architectural scaffolding that gives static text dynamic autonomy. But cycles themselves can also contain inner cycles. When we nest an inner iteration inside an outer iteration, a single-dimensional process multiplies, generating complex, multi-dimensional grids. True software efficiency requires an engineer to move beyond basic syntax. mapping hardware memory limits and strict mathematical laws directly onto the code architecture. This diagram shows a basic age check for a voting system. On the right, the logic splits into a green yes path for anyone 18 or older and a red no path for anyone younger. Every real-world software system relies on this kind of conditional gatekeeping. To write this exact decision in C++, we use an if-else statement. The rule we want to check, age is greater than or equal to 18, goes directly inside the parentheses. The action we want the computer to take goes inside the curly braces, which define a specific block of code. The compiler evaluates the condition inside the parentheses as strictly true or false. With an input of 20, the condition evaluates to true. The program executes the code inside the first set of braces and entirely bypasses the false path. Simple true or false checks form the absolute baseline of software routing. But as systems grow, choices multiply, requiring us to build control structures that handle multiple overlapping conditions. If you forget that else-if structure is a sequential execution model, if we need to assign a student a grade of A, B, or C, the logic checks each block sequentially. The program moves down the conditions, skipping any false conditions, and executes the code block only at the first step that evaluates to true. Writing out conditions step by step works when making a single evaluation, but if you need a program to print a number or evaluate a student's grade 10,000 times in a row, writing 10,000 lines of sequential code is physically impossible. This tracking interface demonstrates a while loop, which acts as a programmatic cycle. To work, it requires 3 absolute rules: an initialization to set a starting value, a condition to tell it when to stop, and an updation step to move the count forward after every cycle. If you forget that updation step, the condition stays true forever. The program hangs in an infinite loop, trapped on a single line of code that never completes. To prevent this structural failure, C++ gives developers the for loop. It compresses the initialization, condition, and updation rules into a single, highly readable line of syntax. By using loops, programmers can scale computational tasks infinitely without expanding the physical footprint of the code itself. We can combine these tools to solve complex mathematical problems, like identifying a prime number. A brute force approach is to write a loop that tests if our target number is divisible by any integer from 2 all the way up to n-1. Inside the loop, we track a Boolean variable called isPrime. If our target number cleanly divides by any integer, the number is not prime. We flip the Boolean to false, and use the break keyword as an immediate command to stop the loop entirely. But testing every single integer up to n-1 wastes immense processing power. Look at this list of factors for the number 12. The pairs multiply to form the target number, but notice what happens in the middle. Once we pass the square root threshold, the exact same factors simply flip and repeat. We translate this mathematical threshold into our code by changing the loop condition to I times I is less than or equal to n. This forces the loop to stop executing the exact moment it hits the square root threshold, entirely eliminating the redundant checks. Limiting the search to the square root ensures the algorithm remains fast, even when checking numbers in the millions. Linear repetition solves flat one-dimensional problems. To operate in 2 dimensions, we place one loop directly inside another. In programming, this is known as a nesting. This 2D grid construction sequence shows how nesting operates. The outer loop controls the vertical rows. For every single step the outer loop takes, the inner loop completes its entire horizontal cycle, stamping out a full column of stars before the process resets for the next line. This hierarchy of loops table categorizes your entire iterative toolkit. Use the for loop when you know the exact count. Use the while loop when you are relying on an unknown stop condition. And use the do-while loop when the code block must execute at least once before the condition is checked. Data grids and building responsive program flow.